Hello, Tanya Laird here, and welcome to part 2 of Lecture 9 of ENGR 231 Engineering Statics. In this part of the lecture, we are going to explore some items related to trusses and truss theory. So in part 1 of this lecture, we looked at what a truss member is, what the truss member condition is, and we defined it as a member that has pins at both ends, is perfectly straight, and has loads applied only at the joints. And when you do that, based on just simple rigid body equilibrium, you can see that it will only carry a single axial force, either tension or compression. So with that in mind, I would like to discuss basic truss theory. So, truss theory. So let's look at truss theory. And in particular, when I say truss theory, in this lecture, or in this portion of the lecture, I'm just going to go through some discussions of, types of trusses, planar versus spaced trusses, simple trusses, some of the advantages and disadvantages of trusses, and some other related topics. So, as you might have guessed, a truss is a framework made entirely what I have referred to as truss members. As previously defined. Now, the reason I separate that out specifically as a specific type of member is that you can have frameworks where some of the members are truss members, but not the entire framework. You might have a frame that is largely made, or a frame or a simple machine that is made largely of things with fixed connections, or members with fixed connections, but there might be one or two truss type members in there. And I like to define that, when I teach statics, I like to define that member support condition, just so I can reference that when discussing frames and simple machines. But if we have something that is made entirely of truss members, then we have what I call a true truss. So that is a true truss. And like everything else, this is going to be an engineering model, an idealization, etc. But a truss, of course, is one that is made entirely of truss members. Now, with that in mind, what are we going to have for a truss? Well, we're going to have a framework, which is a collection of truss members. And if you notice, all of the joints are going to be straight members with pin joints, but connected at their ends, and with no intermediate loads and no members continuing through joints, basically. So let's just draw one of these out. Let's see, what else can we mention about this? Yes, one quick thing. When drawing trusses, often if you're not too careful, especially when you're learning this for the first time, you may confuse, I've had students confuse truss joints with, or pin joints with pin supports, or even rollers in this case. The key difference between a roller support and this pin joint here, even though they're both drawn in circles, is that they have a surface usually underneath them. But again, don't confuse those two. Unless there is at least as I draw them, unless there's a surface underneath them, assume these are pin joints rather than rollers. And in fact, often to avoid that confusion, what you'll see me draw trusses as is something just simply like this. Often I don't even draw the pins at the joints. It's just kind of known from context that if I am doing a problem involving trusses, then those joints are going to be pins. So when I'm working with trusses, unless otherwise stated, again, if I'm working with trusses unless otherwise stated, the joints should just be assumed to be all pins. Now, as we mentioned before, the members must be straight, regardless of what I've drawn here, regardless of how the drawing looks, and the forces must be applied entirely on the joints. So they have to be applied. Now, they can be applied in any direction. They can be applied in any direction on the joints. There can be any number of them, but they must be applied on the joints and nowhere else. And so we can have as many of them as we want, and they can be in any direction we want, but they do have to be applied at the joints. The moment I apply a force somewhere that's not on the joint, like for example this one here, that is no longer a true truss, and so we cannot use the tools that we're going to learn later on to analyze these frameworks. Alright, so that's all well and good, but what are some types of trusses? Let's consider the various types of trusses. Oh, and I should also mention again, this is an idealization. I do want to just really pound that home. Because again, there can be no such thing as a purely pinned joint. There's always going to be some friction present. And in terms of what these actually look like, what the joints actually look like in trusses, often they're gusset plates. And a gusset plate will maybe look something approximately like this. So imagine you had a steel plate cut into something like this. And connected to that, you would have a series of long, slender members. And that's another characteristic of trusses. They tend to have members that are rather long and slender, at least compared to beams and columns and that sort of thing. So you have a series of members coming in here and connected with, even to something as simple as just basic bolted connections. Now, you usually don't actually have literal pins sitting here, like literal lubricated pins that are machined, to be smooth cylinders, that sort of thing. That's what I would consider to be a true pin. But when we talk about this as an engineering model, when we talk about pin joint, we're talking about relative strength. If you look at the bending capacity of one of these members, if I take one of these and bend it until it breaks and measure what type of bending moment is required to break it, and compare it to the bending capacity of this joint, I will find this has way, 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 way more bending capacity than this joint does. So relative to the joint, this is effectively a zero moment connection. So just like everything, these are models, these are approximations. This is just something that is common in statics and other forms of engineering. Now, let us consider some subtypes of trusses, or some types of trusses, or ways of classifying trusses. The main way of classifying trusses that I first want to look at is geometry, or maybe 2D versus 3D. And in particular, or specifically, this would be referred to as a planar truss, or a 3D truss, or a space truss. A space truss is one that has members in more than 2 dimensions. So if you imagine, now I'm going to try to draw a poorly drawn tetrahedron. And so if you imagine having members that meet up in a tetrahedral shape, for example, and then imagine connecting a series of these together, that would be a space truss. And those do have certain advantages, especially for large spans, very large area roofs, and things like that. Space trusses do have their applications. But planar trusses are what we're going to mainly look at in this class. This is where all of the truss, or all of the truss members, are aligned along a single plane. And so when you see me draw trusses like this, we're typically talking about planar trusses. Now, that doesn't mean there's only one of these trusses in a building or a bridge or something like that. Often when you build a bridge, for example, you may have 2 major trusses going down the length of the bridge. I'm looking down on a truss here, and there'd be another truss over here. But both of them would be a single planar truss. And then on base, you might have stringers going between them, various elements that go across, and then some bracing, almost forming a lateral truss as well. So you can have something with an overall frame, an overall structure that's made multiple trusses, but each truss itself is not spanning between multiple planes. Each truss is just occupying a single plane. Okay, so there's that. And so that's 2D versus 3D. Again, in this class, I'm going to focus mainly on 2D trusses, or planar trusses. But even among the plane trusses, there are a whole bunch of different ways of describing trusses. There's roof trusses, which often have their own aspects of design. There's bridge trusses, which have their own kind of thing, their own unique characteristics. We are not going to get into the nitty-gritty about the individual minutiae of types of trusses. Like you can read in your text about all sorts of different families of trusses. There are all sorts of different ways of classifying them, and different names of trusses, like Howard truss and all this kind of thing. And you can study those if you wish, but honestly, it's one of those things that is useful for maybe trivia, or useful for a history of engineering, or if you are actually doing a lot of truss or roof truss design, then you would definitely want to know the types of trusses. That would be when it would be very useful. But for this course, I'm not going to ask you to memorize a bunch of different types of trusses. We are using this mainly as a way of teaching basic structural analysis. And so I want you I'm going to teach you about trusses at a very generic level. So But one type of classification of truss, one further type of truss classification I would like you to be aware of is simple trusses. So let's consider simple trusses. What is a simple truss? Well, a simple truss really starts with a triangle. So think about a triangle. A triangle is intrinsically one of the most stable shapes in nature. If you have a triangle made of 3 members, it is intrinsically one of the most stable and light and most efficient shapes you can have. So if I pull out a triangle in different directions, it is going to be able to resist load in any direction, and mainly and only through its own internal geometry. It is the simplest shape that is stable with its own geometry, even with pin joints. But imagine something like a square. If I have a square with pin joints, and then I try to apply load to it, what happens? Well, if I do that, if I apply a load here and here, this thing is going to deform. It's going to form, it will stretch like this. It will widen out, kind of like this, stretch out, and get thinner in the middle and longer at the edges, along the axis of the force. So a square is not capable intrinsically of resisting force. If I want to have a square, for example, a building frame, if I want a square with no diagonal bracing, if I want that to be stable, I either have to have moment connections at the base, or if I want these to be pins, I would need to have moment connections on the corners. A moment connection is one, of course, that is able to resist large amounts of bending or moment. So there's that. But we see that a triangle fundamentally is one of the strongest, most stable shapes, and it is also completely statically determinate. Now, a simple truss is a truss basically made entirely of triangles. Is made entirely of triangles with no member that continues through an intersection. Or more specifically, the best way to determine if a particular truss is a simple truss is if you can do the following. To tell if a truss is a simple truss, do the following. 1. Draw a triangle. 2. Repeatedly add a joint and 2 members, or just a joint and 2 members to make a new triangle. A new triangle. I cannot write today. A new triangle. And then 3, if the truss in question can be drawn this way, or just if a truss can be drawn this way, it is a simple truss. And I'll show you what this means. And not all trusses can be drawn this way. So if you have a truss here, a truss triangle here, let's start with a single triangle. And for this, I'm going to go ahead and draw the pin joints there. Now, I'm going to add a member, a joint, and a member. I'm going to add a member, a joint, and a member. So each of those is basically adding another triangle to an existing triangle. A member, a joint, and a member. A member, a joint, and a member. And it doesn't all have to be up in one line. I could also add another member, a joint, and a member. As long as I can draw a truss entirely by this method, it will be a simple truss. Now you can have other types of trusses, but if you can't draw it like this, then it's not a simple truss. Okay. So next, I would like to look at some equations of truss, determinacy, and stability. So let's consider this. That'll be our next topic. We'll designate that in green. Truss, determinacy, and stability. So we're going to look at a truss, or we'll be looking at many trusses actually. And I'll go ahead and draw the joints on here. And let's just give it a little bit of size. I'm going to draw this truss, and then I'm going to show how it would look in different cases of determinacy and stability. Actually, maybe I'll just keep it to a simple number of members. That would be relatively easy to count and get through because this is just a basic example. And so we have our roller support and a pin support. Now, I should mention that I've been drawing these trusses as simply supported with a pin on one end and a roller on another, but they need not be that way. I could just as easily have a truss like this, where there's maybe a pin support here, a roller support here, and maybe members like this, that joining there, that roller there, and maybe having this, I could have this keep on going for another bay or two, just something like this. This would be a cantilever truss almost, or I could have a truss that's hanging from a wall. That's perfectly possible if you have a strong enough support. So you could have maybe a pin there and a roller here, and I could have something like this here. I might hang loads down or something like that. That would be like an awning or that would be like an awning or maybe like a sign on the side of a building or something like that. All right, so the key to these equations is to realize that when we work through truss equilibrium, at least when we look at the method of joints, which will be in the next portion, actually next portion lecture, portion 3, we are going to analyze each joint at a time. And that joint we are going to analyze as a point particle. Joints are effectively point particles, or are treated as point particles. If you look at the examples and problems in your text, you will see that they never actually tell you, oh, a joint is 6 inches across, or 8 inches across, or 4 inches across, or whatever the dimensions of the gusset plate are. And the reason for that is that the dimensions of the gusset plate, or whatever the connection is connecting the truss members together, is not important. And the reason for that is that we are treating the joints as idealized point particles. So we are actually going to use, we're going to do equilibrium equations about each joint. And so if we just like any kind of two-dimensional point particle, we'll have equilibrium in the x direction and equilibrium in the y direction. We'll have an equilibrium in the x direction and an equilibrium in the y direction. And together, we will use these as equations of equilibrium to solve for unknown forces in a truss. So basically, each joint provides two equations of equilibrium. Each joint provides two equations of equilibrium. And so those are basically our equations to solve for unknowns. And what are our unknowns? Well, the unknowns that we're concerned with are member forces. And remember, each member will have a single force in it, either positive or negative, tension or compression. But as we saw previously, a truss member is capable of carrying only a single axial load. So each member effectively represents one unknown. And if you add another member, you add another unknown. You remove a member, you remove an unknown. And then the last one is reaction forces. And so if you have a fixed support, that will be 3 unknowns. Although that's tricky to see how you'd have that on a truss. But if you have if you have a pin support, that will be 2 reaction forces, so 2 unknowns. and a roller support, that would be 3 unknowns. Also, be very careful on the number of joints. Don't double count things. So sometimes sometimes you might see a truss drawn like this. If you just have a truss, for example, here, you might see a truss drawn like this, but then with a pin support underneath. This does not mean, or sometimes I see students draw them like this and then say, oh, this is 1 joint, 2 joints. Well, in reality, we probably should draw it more like this, with the roller, with the pin baked into the pin joint. You don't have 2 things here. These are basically the same exact thing. It's more like you have your gusset plate also touch the ground or something. That's effectively what we have here. So basically, a joint is just a location where 2 members happen to meet. So make sure you don't confuse the 2 there. Now, the equations that we'll be looking at are simple inequalities. Well, and one equality. So 1, if m plus r is equal to 2j, this is a system in balance. This is statically determinate. In this case, your number of joints is the number of members plus the number of reactions is equal to twice the number of joints. In other words, the number of unknowns is exactly equal to the number of equations, because remember, each joint provides 2 equations of equilibrium. So if you multiply the number of joints by 2, we get our total number of equations, and if the number of unknowns is exactly equal to the number of equations, we have a statically determinate system. So let's consider this one here, this truss up here. The number of members would be 1, 2, 3, 4, 5, 6, 7, 8, 9. So we would have 9 members. The number of reaction forces, we would have 2 on this pin and 1 more on this roller support, so plus 3 for our R. And the number of joints, 1, 2, 3, 4, 5, 6. 6 joints, so 6 times 2, 12 equals 12, and this is statically determinate. And this shouldn't surprise us, because this is actually a simple truss. I draw it by first drawing this one triangle, then add another triangle, and add another triangle, and add 1 more triangle. So yes, it is a simple truss, and all simple trusses are statically determinate. Now, what if m plus r is less than 2j? Well, if m plus r is less than 2j, our number of unknowns is less than our number of joints, and this becomes, it will stay statically determinate, but more importantly, it becomes unstable. And really, in particular, it will be either internally or externally unstable. In fact, maybe I'll just write that as internally or externally unstable. Or externally unstable. And I'll show you what I mean by each of these. Internal instability means if I'm will primarily occur if I'm missing a member. So imagine this truss up here. Let's see, actually, maybe I'll draw a slightly different truss here. And I got some triangles here, keep adding these. So you start out with a simple truss. And this, as shown here, would be statically determinate. I would have m plus r being equal to exactly 2j, because again, members for this case, members would be 1, 2, 3, 4, 5, 6, 7. And let's see here, the number of joints would be equal to 5. Well, the number of joints would be equal to 5, and the number of reactions would be equal to 3, so it would be exactly stable. However, what happens if I remove this member here? Now, the number of members is 1, 2, 3, 4, 5. Sorry, 6. 1, 2, 3, 4, 5, 6. I can't count. The number of reaction forces is equal to 3, but the number of joints is still 5. So in that case, this is unstable. The number of m plus r is less than 2j, but in particular, is geometrically or internally unstable, because this thing now has a collapse mechanism built into it. What happens if I apply a load downward? Well, this thing's just going to basically cave in on itself. Look at this. it's going to want to rotate down, and there's not going to, this member is going to want to move toward this member, and there's not going to be really any member here to resist that collapse. So this is just an extremely unstable truss. Now, an externally unstable truss would be one where, let's say I drew the same truss, and maybe it's geometrically stable in the sense that it would be able to resist deformation of the frame itself, but maybe it has, what if I remove one of the reaction forces? In that case, if I remove one of the reaction forces, well, now there's nothing keeping it nailed down. If I just have a set of rollers here, roller here, and a roller here, if I pull this thing along, it's just going to go wandering off. Or we could also have an example of internal instability that is kept stable. It is possible to have a truss that is kept stable, but it's not actually geometrically stable. So if I have a truss here, what if I have something like this? Consider something like this. This would be an example of internal instability. Because imagine let's look at what I have here. Sorry, I removed this one. Here, m would be equal to 2, j would be equal to 3, and reactions, well, actually I should say this would be internally unstable, but the interesting thing about this is it would still be, I guess, overall stable, but I would not call it geometrically stable, because this is not geometrically stable, because if I remove it from its supports, it would still have a tendency to collapse. But in other words, its own framework is incapable of holding it in place. But if I had those reactions, I could hold it in place. But anyway, that's the basic idea. And then finally, if m plus r is greater than 2j, here you have a truss that is statically indeterminate. It is most likely still stable, but it is statically indeterminate. So this one I would just call geometrically unstable, even though it still satisfies the equation m plus r is equal to 2j. So sometimes you get really weird trusses like that don't generally follow the rules, in that they do follow the rules of it being statically determinate, but this basically guarantees that it's internally or externally unstable. But it is possible to have cases where that's not true. It is possible to have cases where m plus r is still equal to 2j, even though it is geometrically unstable, and that's mainly when you have more than 3 reactions present, or you have some clear collapse mechanism built into it. Statically indeterminate, however, is very common, especially when you have trusses that have members continuing through joints and such. So for example, imagine I were to make a truss like this. Let's say I have a pin. Let me draw this a little bit bigger. Like this. A pin and a roller. And then something like this. And I'll have this member go right through, these members go right through each other. So what I mean by that is, at that middle joint, there is no actual joint. Basically, one member goes right through the other. And how that would likely happen is one member is slightly behind the other in 3 dimensions or something. So in this case, the number of members would be 1, 2, 3, 4, 5, 6. So we have 6 members. The number of reactions is 3. And the number of joints, though, is just 4. So m plus r would be equal to 9, and 2j would be equal to 8. So m plus r would be equal to 2j. You would not be able to fully solve for all the forces in this truss because it is fundamentally statically indeterminate. Now, you could solve for it using some of the laws of mechanics of materials and structural analysis, but for that, again, you would need to know things about its cross-section, you need to know cross-sectional properties, material properties, and a variety of other things. All right, so there's that. And finally, I would just like to briefly discuss some aspects of truss efficiency and truss advantages and disadvantages, or just probably not efficiency, but just in general, some aspects of truss advantages and disadvantages. Why do we use trusses? What are some of their benefits? Why do we see them a lot in trusses? And what are some of their downsides? So truss advantages and disadvantages. That will be our final topic for this portion of the lecture. Now, so first let's look at their benefits. Well, one of the main benefits of trusses is that they are intrinsically efficient. They're highly structurally efficient. There's a reason we tend to use them quite a bit. And you see them everywhere. You see them in buildings, you see them in structures, you see them even in things like radio towers, you see them in offshore structures. They're used all over the place. And the reason for that is they are highly structurally efficient, especially when you need to cross large spans without using a great deal of weight. Pound for pound, it's really hard to beat a truss in terms of weight performance. They're highly structurally efficient. Also, they have simple connections. Simple, easy to form connections. Easy connections. What do I mean by that? Well, if you remember my previous label or drawing of a gusset plate, now they don't have to be octagonal or semi-octagonal like we had before. In some cases, they are just plates. So I could have something like this. Imagine I just had a series of members coming together with just a couple bolts in it, and that's really all you need often. So you might have nothing more than just a couple bolts in a gusset plate, and that's it. That kind of connection is easy to make. That's incredibly quick, incredibly efficient. You just drill a couple holes in the plate, you drill a couple holes in the web flange of your angle irons or whatever they are that the truss members are made of, and then you have a truss connection. Relatively simple. Compare that to a moment connection you'd have in a beam. So often, if the alternative to using a truss to span a gap is to use a beam, like a large W section or something, and that beam would have, a wide flange, or that beam would have a flange and a web. It would have flanges and a web, like we discussed previously. And if you want to use if you're going to need to use a moment connection, the connections can be quite involved. So instead of just a simple bolted connection, if you want to connect one, let's say you want to connect this beam in a moment connection to a column, you're going to have to do a lot of things. First, you're going to need a way to connect the web to the column, and so you're going to need a weld here, and the couple bolts or welds here. You're going to need a plate that connects the top plate or the top flange to the column, maybe a weld here and another weld here. And then you're going to need a third plate on the bottom flange to connect this, maybe a weld here and a weld here. So I'm looking at basically 1, 2, 3, 4, 5, 6, about 6 different connection points that would have to be either bolted or welded. This is a very difficult connection to make, especially if you're making it, 100 feet in the air. That's not easy to do. It takes a long time, and it takes skilled labor. Not that this can be done by somebody without any skills. This takes skills as well, but this is a lot more involved. The nice thing about trusses is they are very quick to put up. They're very quick to connect. The members are very quick. Also, for many applications, the trusses they have enough internal rigidity that often entire trusses can be built off-site. Off-site construction is a big benefit often. You see this a lot, especially in residential roof construction. If you've ever seen a house going up, if you or your family has ever built a house, especially a wooden house, often what you'll see the house frame will be, for a stick-built home will be built, on-site, built in pieces and modules and raised up and things like that. But the roof trusses will often actually be brought in on the back of trucks. They'll be made in a factory somewhere where they can be made to very, uniform conditions. You'll buy a truss for a certain span. Maybe actually you might even design your entire major portion of your home layout based upon what roof trusses are available in some cases. And so you'll just go to a catalog and say, okay, I want a truss that is this span and can carry this amount of load, and you order one from a catalog and it shows up on your construction site, and there's a roof truss. Very efficient. A lot more efficient than trying to build something on site. You save a lot of time, effort, and most importantly in construction, money. You save a lot of that if you can if you can just order a roof truss from a catalog. And so those are some of the benefits of trusses. Now, you still have to pay the piper though, and there is no such thing as a free lunch, so there are some drawbacks to trusses. Otherwise, we would only use trusses for everything. So let's discuss some of the drawbacks. Some of the drawbacks. Now, you can have indeterminate trusses, but generally trusses, I think most of the times I think of trusses as determinate, but oftentimes they have very little redundancy. We discussed this previously when we looked at statically determinate objects. Often trusses have very little redundancy. So in other words, if I have a simple truss, especially for a simple truss, if I have a simple truss, I can find out, because it's statically determinate, I can find out the force in every single member. Now, the reason fundamentally that I can do that is that there is only one possible load, only one possible path, one possible load path for loads to be carried through the structure. So, if any single member is removed, well, let me draw this as individual members to drive the point home. It doesn't help if I draw them all as one member. If any one member is removed, if I remove just one of these members, now this thing's just going to fall over and collapse completely. Like, this joint is not a moment support. It's not a moment joint or a fixed connection. This thing's just going to flop right on over. And so I need every single member in that truss. So it really becomes a case of a chain that is as strong only as its weakest link. If you lose a single member on a major truss, that entire structure is going to collapse. So the member design in trusses become very important, and especially the connection, especially the connection design. If your connection fails, if you have just two bolts holding a major truss member in place, if one of those bolts fail, or both those bolts fail, that entire bridge may be coming down. Now, in certain systems, especially if you have, especially for things like roof trusses, where you might have a whole bunch of trusses all in a line, if one member fails, then maybe one truss can shed load to its brothers. But if you have a major bridge and there's only one truss or only two trusses holding that entire bridge deck up, if one of those goes, the whole thing is probably coming down. So trusses, they are very efficient, but one of the downsides is that they have very, very little redundancy. Now, trusses, actually there's one thing that is going to be a bit interesting that I should probably put both in the benefits and drawbacks category, and that is slender members. Because the members only carry axial load and not any kind of bending moment, that means that you can have them be very slender. In other words, very thin relative to their length. And one of the benefits of that for slender members, especially for structures that are outside, is if your members are very thin, this means you have very low wind loads. They don't have a lot of surface area. If you have a bridge with a big bridge truss or a bridge frame or whatever it is, every square inch of your members are going to be gathering wind load from the wind and from rain and everything else. So the thinner they are relative to their strength, the less wind load you're going to have, which is beneficial. But slender members are also a drawback. They're one of these this is an interesting property that's both a benefit and a drawback. So have a few major concerns. First of all, buckling, which is a bit beyond the scope of this course. This is something you'll see in mechanics materials. And actually, I'll probably have many of the students in this class later in the summer from mechanics and materials. But buckling. Buckling is when when a compression member, like a column, if I apply force on either ends, and it just kind of bows, when it fails, it just kind of bows out like that. Well before you reach the limit of the material's strength, it actually fails geometrically, with the end of it just popping out to the side and failing quite spectacularly, actually, because it's a brittle failure. And so buckling, and slender members are very prone to this. So often in trusses, you have to add buckling support to some of your longer, more slender compression members, not for member strength, but just to prevent buckling. What else? Corrosion is a major concern. If you compare a steel beam, a big steel beam, to a truss, the members are going to be a lot thinner. So a truss from the side, to carry the same load, you'll probably have a truss with a thin top chord member and a thin bottom chord member, with then some elements. This is basically looking at a planar truss from the side. If you look at it from the side, you'll see this. You'll see a thin member up here, a thin member up here, basically maybe tubular members or maybe angles or various thin slender elements, this kind of thing. And so thin slender elements, thin elements with thin structural shapes they have most of their surface area, they have most of their volume relatively close to the surface area. So if you have a big old beam, with a 2-inch thick flange or something like that, think about that. If you have a big beam with, say, a 2-inch thick flange, at the center here, the center part of that steel is an entire inch away from the surface. But what happens if you have a little thin angle iron that the thickness is only half an inch? It's only half an inch thick. Well, that means at any point in that member, if this is only half an inch thick, if that web there is only half an inch thick, that means that at any point inside that, there is no point or there's no atom of steel that is more than a 1/4 inch away from the outside. And that becomes important for corrosion, because corrosion tends to work its way from the outside to the inside of members. And so if you have a big beefy member, it's going to intrinsically be more corrosion resistant pound for pound than a truss of the same strength or weight, simply because it has stockier members. Basically, it has thicker elements, and that you are basically hiding more of your surface area further from the outside, which makes them more resistant to corrosion, even if you use the same corrosion protection method. So if you are doing any kind of trusses, now this isn't as important for many, in certain cases, especially for like interior building trusses, but if you are in a corrosion prone environment, such as like an offshore oil platform or something, you will absolutely need to have to worry about corrosion protection if you're doing any kind of deck truss or something like that. And so corrosion protection is much more important for truss systems than other types of systems, but that's something offshore engineers are very familiar with. Now, finally, one area that is under slender members that they don't often think about is fire. Fire is an interesting one. In fact, I might even discuss this on another slide, because I do like to talk about this. It's kind of neat. Trusses and fire. Now, I have a riddle for you. Consider two different roof systems. Let's say I'm in a relatively large building, and I could be in a building that is supported by two different options. One is a roof truss, like a steel roof truss. It's a steel roof truss, so it's a truss like this. Both of these would have let's say I'm designing a roof truss or a roof supporting system, or let's say I could be in a building with two different types of roof support systems, and I have a choice what type of roof system it's going to be in. Basically, for some crazy reason, evil leprechaun, evil genie has said, you're going to be in a building fire, but for some crazy reason, I'll let you choose what type of roof system of the building that you're in. But I know this is really stretching credulity, but anyway. So I have to be in a building that's on fire, but for whatever reason, I get to choose what type of building that I'm in. And the roof truss, well, its members are going to be very thin angles like this, thin angle irons, that kind of thing. Maybe I have an angle iron like this, an angle iron like this, making up the top and bottom chord of the truss. Or maybe I have like thin hollow square structural tubing with then some thin angles running between them or something like that for the diagonals and for the verticals. So relatively thin members. Each member is no more, and this would be hollow here. So something kind of like this. So there is basically no steel that is more than half an inch thick. Basically, I just have a whole series of thin members, but this is pretty strong. Now, this is very strong. This is still a strong steel truss. It's going to have plenty of strength to carry the same amount of load over the same span. Imagine I were to do this with a wooden beam. If I were to carry this with a wooden beam, the same load for a very large span, like let's say it's a fairly large span, like 50, 60 feet, something like that, to carry that kind of bending moment and shear, I'm gonna need a big honking wooden beam. I'm gonna need a big old, built up wooden section, a glulam member, something like that. Maybe something that's like 18 inches by 24 inches. This big, strong, huge, monstrously bulky, beefy wooden beam. This big old thing, 8 inches by 24 inches of just solid pine or solid oak or something like that. Big honking thing. And you do see these in certain civic buildings and certain residential buildings and things like that. So here is the riddle. Would I rather be in the building with a steel roof truss, or would I rather be in the building with the big giant wooden beam. Now, many students who are, and many people who are not familiar with some of these engineering principles, will wonder what kind of question is that. Obviously, if I want to be in a building on fire, if I no, I don't want to be, but if I have to be in a building on fire, I don't want to be in a building that's the roof is being held up by wood. Obviously, that seems so obvious. Well, as you probably figured out, it's kind of a trick question, because if I had to choose between the steel roof truss and the wooden beam, and assuming this was a pure steel roof truss with nothing else added to it, I'd rather be in the building with the big wooden beams holding up the roof. And the reason for that is that, yes, wood will of course burn, but you have to think of this in terms of surface area to volume ratios. See, a lot of people don't know how steel behaves, or really any metal behaves, under heat. Some people think that metal has this kind of behavior, where it's like strength, here's your strength versus temperature. They kind of think that strength is just constant, and then it just drops to zero when you hit the melting point. This is not how steel behaves. This is not how any metal behaves. It's not how any solid behaves. Instead, what tends to happen, if I were to draw it now, I'm gonna, because this is not a mechanics of materials course, technically I shouldn't say strength versus temperature, I should say something like yield stress, but I'll keep things relatively simple and just say strength versus temperature. So what really happens is you get kind of, for most temperatures it's fairly constant, for initial temperatures it's fairly constant, so right at the beginning here we're constant, but as temperature increases, the strength starts to decline. It goes down, 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 and then only at the end does it rapidly drop off to zero. And that point there is what we call the melting point, where you lose the last bit of cohesion and you lose all of your strength, what little bit of strength you have, and you lose that relatively quickly. We call that the melting point. But in reality, by the time you get anywhere near the melting point, you've already lost, a quarter, half, 3/4, maybe even 80% of your strength well before you got to the melting point. And buildings, they do have some amount of factor safety built into their design, but they don't have so much factor safety that you can just remove half of their strength or 3/4 of their strength and still have their strength retained. And so the thing about these very thin, slender members, if I have a very thin angle iron, for example, when I put flame underneath that, if I start applying heat to this, that thing is going to instantly heat up almost all the way through. For one, steel is a metal, which means it's a very good conductor. And so the inside temperature is going to basically be exactly the same as the outside temperature, only slightly different. It's going to quickly heat up the same temperature as the outside air. And so whatever temperature the air is outside, the interior metal is the same. And so the air temperature, that if you're in a building that is on fire, well, get out of the building instead of pondering structural analysis and engineering statics. But if you're, don't stand there and wonder, oh, I wonder if this is a wooden frame or not. Please don't do that. I don't want to be responsible for your timely demise. But anyway, so that's grim thinking. But if there is, again, if there is a very light, slender elements, the air around those elements is going to rapidly heat those members up to the same temperature as the air. And if that temperature is hot enough, or as that temperature rises, it's going to cause the strength of that material to weaken. And if it gets up high enough to the point where that member can no longer withstand the heat, or can no longer hold up the load, hold up the roof above it, it is going to collapse. This is often why building roof and floors collapse during fire. It's not that the structure, it's not that the fire heats the members up to the point of melting. No, they just get to the point where they've lost most of their strength, they can no longer carry the load they need to carry, and the whole thing comes tumbling down. And when one of your trusses on your roof collapses, well, normally if one truss were to fail in a roof system, or especially like a building floor, there's usually one right next to it that can carry the load. But if they're all weakened, the moment one of them collapses, they're all going to collapse because they have to carry further and further load. You get a progressive collapse. Okay, so that's easy enough to understand. What about the big honking wooden beam? Isn't the wood beam just going to burn up? Well, absolutely. However, fires don't burn forever, and wood is a very poor conductor of heat. If you've ever tried to put a great big log in a fireplace, you know that it takes an awfully long time for a great big wooden beam to burn. It takes a very long time for a big wooden beam to burn. Especially, now, I've never tried to burn a log or a piece of wood that is 18 inches by 24 inches in a fireplace. I don't know if I've even had a fireplace that would fit in there. But if I tried, I mean, it's going to take you all day to burn through that thing. So yes, if there are flames and heat and things like that around that great big honking wooden beam, yes, it is going to burn, but it's only going to burn on the outer layer. Basically, what has to happen is that heat has to slowly work its way into the framework. And so basically how it works is it would have to char the outer layer, transfer heat to the next layer, char that, and then one layer would get charred, maybe fall off, then another layer would get charred, you have to get charred, and then it would fall off, and so on and so on. But it's going to take you hours to burn through that, burn all the way through that. It may take you all day to burn all the way through that. But fires don't last forever. For one, the fire department will hopefully be coming by to put the fire out. And again, the idea is that you're not going to stand underneath the roof waiting for the thing to burn out. No, you're going to get the idea is not to design a building so that it can last indefinitely under fire. You're just trying to make the thing last long enough that you can get out of the building. If the building collapses, 5 hours after I got out of it and everyone got out of it, well, I'm not terribly concerned. It's loss of property and belongings and such, but nobody's getting killed. We care about whether the building, what we also care about as engineers, is whether the building falls in on somebody before they can get out. And so, this kind of system here, it takes so long for this to burn that people have a lot of time to get out of the building. And the same thing is true for big concrete beams or even like steel beams, where you have great big, heavy, hefty steel sections, like inch and a half thick, inch thick flanges, that sort of thing. They're not burning, but they take a long time for that heat to work its way into the core of the member. And so they have the same kind of thing. And so, again, you may end up burning up the outer layer of the wood, but one of two things usually happens first. Either the fire department comes and puts the fire out, or the fire has finite fuel. It runs out. There's only so much stuff lying around to burn. If in a building in a house or something, what is available to burn? Well, you have carpets and drywall and doors and furniture and things like that, but there's only so much of it to burn. Now, you obviously don't have these type of big honking wooden beams in a residential structure. There you have a wooden roof truss, which is honestly the worst of both worlds. You have slender elements and wood, so that would be my least preferred type building to be in a fire, but those are designed for fire safety as well. But for large structures like large commercial buildings, large educational buildings, that sort of thing, if you're using roof trusses that are made of long, thin, slender members, you are actually required to add fireproofing. And so what fireproofing looks like is like this. It's like basically it's a form of cementitious, very foamy kind of concrete. So if you have your truss members here, basically it's kind of like shotcrete, if you're familiar with the term. It's a very foamy version of that. So you have your truss members that are very thin, I'm kind of drawing this out roughly. So you have your truss members here, and basically it's just pressurized it's pressurized kind of in just a pressure vessel. It's basically just a shotcrete type system. You just spray it. It's just a spray foam type system, basically. Essentially, just imagine spray foam, except more like concrete, and it hardens into a very. It basically after it hardens and cures, it's basically like a very foamy, almost styrofoam-like concrete, a little denser than concrete or than styrofoam, but not anywhere near as dense as ordinary concrete. Maybe I think to illustrate this, just start by drawing an ordinary truss. So basically, what they do is the normal truss members are too thin, or don't have enough surface area to volume. So the idea is to add a lot of surface area without adding a lot of volume. So you just spray all this fireproofing along here, and that greatly increases the surface area of the truss without actually increasing weight all that much. Now, it does increase the weight a little bit, but not by much. And so once the members have been fireproofed, you might have from the side here, if I look at it in profile, you maybe had an angle iron member like this, and originally it was like this, but then you spray some fireproofing on it, and it's a very sticky kind of foam as well. So just kind of, you can just spray it and it kind of sticks there, and it ends up looking all lumpy and poofy like this, almost like cotton candy or something. And so it just kind of sticks there, and now you have something that is it's this again. The filler here is very light, so it doesn't add much weight, but it adds a whole lot of volume and a whole lot of surface area. So now, if there's heat trying to enter from the outside, it has to slowly work its way through, and because it's a very foamy type of closed cell type foam type thing, that acts as a great insulator. So you've taken your truss member that is now that is previously very conductive and very slender, and now turned it into what is effectively a member with a very large volume of surface area, and that volume that does exist is a very great insulator. So you kind of have the best of both worlds now. You have something that's relatively strong, but also relatively good with fire in terms of fire. But the downside of this is nothing is perfect. There is a lot of skill in applying this, and you do have to make sure this is inspected properly and applied properly. There's a lot of art to it and science to it to make sure that's done properly. Anyway, that's a very long-winded explanation of some of the benefits and drawbacks of trusses. I think this will conclude and cover this portion of the lecture. I just want to give you a brief but a little thorough introduction to trusses. Look at some of the types of trusses, discuss how trusses work in theory, look at truss determinacy, and also discuss some of the benefits and drawbacks of trusses. All right, that'll do it for now. Let me know if you have any questions. I will see you for part 3, or I'll see you soon for part 3, where we discuss the method of joints. All right, that'll do it for now. Thank you all for watching. I'll see you all soon. Let me know if you have any questions. And as always, thank you.